بسم الله الرحمن الرحيم. اليوم نبدأ محاضرة رقم 6 في Random Variables Stochastic Processes. المحاضرة بتتكلم عن بعض أنواع ال Distribution Functions. أشهر نوع في Distribution Functions هو ال Gaussian Random Variable أو ال Gaussian Distribution. The Gaussian Random Variable. في كتير من الأحيان بنسميه إحنا normal أو Gaussian. فGaussian كتير من الأحيان بنسميها normal random variable. طبعا هنتكلم عن الGaussian random variable في له distribution معين اللي هو كالتالي: random variable x is called Gaussian or normal if its density function has the form f(x) of x equals to 1 over square root of 2 pi sigma x squared e to the minus x minus a sub x squared divided by 2 sigma x squared. And here x goes from minus infinity to infinity. So this is a random variable that has a density, normal density or Gaussian density, f(x) of x, and those are two constants where sigma x greater than 0 and ax greater than minus infinity less than infinity are real constants. Later on we will see that this sigma x squared is called the variance and ax is the mean. We'll see it when we take the expectation of the random variables. When we take functions of random variables, and one of the specific functions is the expectation. Okay, this function here, the density function, has the bell shape or the normal shape. It's like a bell. It looks like this. So if this is, let's say that this is f(x) of x. So this is my x here, and around this symmetrical line is my ax. So the maximum will be at ax, and the maximum when x equals ax, so this is e to the 0, which is 1, so the maximum value is 1 over the square root of 2 pi sigma x squared. So this is the maximum value. If you go below this by sigma x, so if you go ax minus sigma x, and the same thing is ax plus sigma x from both sides, if x is equal to this, then this is e to the minus 1/2, which is equal to 0.607 over the square root of 2 pi sigma x squared. So it's 0.607 from the maximum value. Below and above ax by the by a distance of sigma x. Okay, so this is how the density function looks like. If we need to see the distribution function of this random variable, it is the integration of the density function. So you have square root of 2 pi sigma x squared. This is a constant, and you have an integration from minus infinity up to x e to the minus z minus ax squared over 2 sigma x squared dz. This is 2. It's not. Okay, so this is the function, and we can see that this function cannot be evaluated analytically. So if you need to find the distribution for a certain x, this is e to the minus something squared, which is really hard to evaluate analytically, and most of the time it is done graphically. But because you have so many ax's and sigma x's also, you'll have a problem to evaluate this function. Okay, let's just take a look at this function, how it looks like. For this one here, it looks like this, you know. The function will be monotonically increasing function. So it will increase like this, and it will approach 1 at infinity, approaches 0 at minus infinity. At the value of ax, so this function actually is f(x of x), the distribution function. At ax, it has a value of 0.5. So you have 0.5 of the probability below ax, 0.5 of the probability above ax. If you have ax minus sigma x, you have here a value of 0.159 and a value of ax plus sigma x, you have a value of 0.841. This is a standard for any value of ax and sigma x. You have this. If you go below the mean or the constant ax by sigma x, you have this value. If you go above by, so this is a standard. Okay. Also for this Gaussian, we also have another notation. We call x with this tilde. X belongs to a normal of ax and sigma x squared. So we can say that this statement means x belongs to a normal distribution with a mean of ax and a variance of sigma x squared. Okay? All right. So this is the distribution function. And this is how the notation that we are using for shorthand notation for representing a Gaussian. X belongs to a normal of ax and sigma x squared. Okay, let's put this statement first and discuss it a little bit. Evaluation of the distribution function for different values of x with so many values. For ax and sigma x squared is not an easy job. So it should be done numerically. Now to do that, notice that if you have ax sigma x, this value is greater than, or can varies from minus infinity to infinity. Sigma x squared is always positive, but it can go from 0 to infinity. So to evaluate a distribution function for so many different values of ax and sigma x squared, it's really something not easy. So to do that, we always transform this into some prototype. This prototype is the normalized Gaussian. So our normalized Gaussian or we call it prototype Gaussian, okay, is x belongs to a normal of zero mean and unit variance. So we'll take this one and make it our reference always. So whenever you have a Gaussian, you have to transform this Gaussian from its mean and its variance to a zero mean and unit variance, and then find the numerical solution that you are looking for. So in this case, we have ax here equal to 0 and sigma x squared equals 1. We will call this normalized Gaussian as g of x. So our g of x is 1 over square root of 2 pi, the integration from minus infinity to x, e to the minus z squared over 2 dz. So this is our normalized Gaussian. Always transform the distribution from any distribution with any ax and sigma x squared to a distribution with zero mean and unit variance, with ax equals 0 and sigma x squared equals 1. Okay, now this makes our life easier because we will find a table, numerically solve the integration, the e to the minus x squared integration, solve it for this one only. When you transform that one to this one, then you find the table, you go back to the other one, and you find the corresponding probability that you are looking for. Okay, so we will make a table to find the numerical integration of g of x. So a table for x greater than or equal 0 is given. For negative values of x, we use the relationship g of minus x equals to 1 minus g of x. A general Gaussian distribution function fx of x can be found in terms of g of x as, okay, so we will see what is the relationship for a general fx of x with this normalized Gaussian, and go to the table and find the corresponding probabilities that we are looking for. So recall that fx of x for any x is equal to 1 over the square root of 2 pi sigma x squared, integration from minus infinity up to x e to the minus x minus ax divided by 2 sigma x squared dx. Okay? Now, I'm gonna do some kind of transformation of the variables, and what I will do here is then I'm gonna let u equals to z minus ax over sigma x. So x, sorry about that. We have to put the dummy variable here. So this is z x. Because the upper limit is x, we have to integrate with a dummy variable, then we substitute the upper limit, so you end up with a function of x. This is how we learned that from mathematics, actually. Use dummy variable for integration if the upper limit or the lower limit is the function of x that we are looking for. Okay, so we substitute u for this here, z minus ax divided by sigma x. So du is equal to dz over sigma x. Okay, so du equals dz over sigma x. If we substitute those in f of x, so f of x will be like 1 over square root of 2 pi sigma x squared times integration from minus infinity. So minus infinity stays the same. This x here will be as x minus, so you have z is the variable, so the upper limit will be x. So you substitute x instead of z, so xz minus ax over sigma x, okay, times, inside the integration you have e to the minus u squared over 2 dx is sigma x du. And this sigma x will cancel with the square root of sigma x. So you end up with 1 over square root of 2 pi e to the minus u squared over 2 du. And this is equals to g, your normalized Gaussian, but not x. Instead of x, it's x subtracted from x, you subtract ax divided by sigma x. So fx of x for any x is equal to g of that x, particular x, subtract the mean from it, divided by sigma x, normalize it by sigma x, and you end up with the prototype Gaussian. Okay, so this is how we are going always to manipulate a Gaussian distribution. Take the x, subtract from it the mean, divided by sigma x, and transform it into the prototype Gaussian. Go to the table, find the corresponding value of the probability. Okay? So the values, as I said, the values of g of x are given as a table. Usually, in so many literature, you will find this table in the following manner. You have x here to be starting from 0, and then you have here in steps of 0.1, 0.2, 0.3, then 1.0, 1.1, 1.2, and then 2.0, 2.1, 2.2, and we continue until 3.1, 3.0, sorry, 3.1 until 3.8, something like this. So if you go more than 3.8, around 4, more than 3 times the variance, which is 1, then you end up with a probability or distribution of 1. Okay, so this is like a matrix. This table is given in a compact form where you have x in the columns here, or in the rows as steps of 0.1, and you have the steps of one part of 100 in the columns. So you'll have here 0.00, 0.01, 0.02, 0.03, 0.4, until 0.05, 0.06, 0.07, 0.08, and at last is 0.09. If you have 0.10, it should go to the next level. So let's say that I need to find g of 2.15. 2.15. If you have a value of 2.15, then the g of 2.15, we have to go to this value here, which is 2.1, and to 0.05 is this value here. So g of 2.15, we have to divide this into 2.1 plus 0.05. 2.1 coming from the rows here, 0.05 coming from those columns, and where those two intersects here is your value. So your value here will be 0.9842. So g of 2.15 is equal to 0.9842. Okay? This is how we find it from the table. So the table here, you have values here, values, and whenever you have g of any value inside, you look at the corresponding value and you combine the steps of 0.1 with the steps of 0.01, and you combine them together and find the corresponding value as we did for 2.15. I will post to you through the Teams the corresponding table so that you can use it every time. All right. So this is how we do the table, normalized table for g of x, and we can use it for any fx of x, which is a normal or Gaussian distribution. Okay. The second type of distribution that I will discuss with you is the uniform distribution. Uniform distribution. The uniform distribution is a random variable x which has the density function fx of x is equal to 1 over b minus a for x between a and b, and 0 elsewhere. Don't worry about the equalities, because this is a continuous random variable, and the probability of a discrete event on a continuous random variable is equal to 0. So whether this one, equality here or here, is not there, or if it is there, it doesn't matter much, okay? So this function looks like this, it looks like this function generally looks like this with 1 over b minus a. And actually, 1 over b minus a is the height of this function. The width is b minus a times 1 over b minus a, so the area under the curve should be 1. Okay? So this is my x. So the area under the curve of fx of x is equal 1 over b minus a, which is the amplitude, times the width, which is b minus a, and this is equals to 1. So it's already settled here. You can use the unit step function. Using the unit step function, I can say that fx of x is also equal to 1 over b minus a times u of a minus u of b, where u of x is the unit step function. Okay? Okay. What about the distribution function? The distribution function of this one, it will be 0 until a, then you have monotonically increasing function until b, and then it goes to 1. So this is 1. The slope here is equal to 1 over b minus a. The slope is 1 over b minus a. Fx of x is equal to 0 for x less than a, x minus a over b minus a for x between a less than b, and 1 for x greater than b, greater than or equal b. Okay, so this is the function. And we say it is uniform because every single value between a and b has exactly the same probability. This is why we have a uniform distribution. We call it uniform distribution because all the values between a and b are likely to happen in the same probability likely, or equiprobable, let's say. So they are equiprobable. Okay, let's move. Just one remark here. There are so many random variables with so many different distribution functions in the world. We have discrete random variables, we have continuous random variables. What I need from you is please concentrate on the Gaussian and the uniform. The others, if I need them, I will support you with the formula for, let's say, the Rayleigh distribution, the exponential distribution, the Poisson, all the distribution that we need. I will support you with those. Please, just you have to know the formula for the Gaussian and the uniform distributions. Okay, I will move to another subject now. It's still within the distribution and random variables, but to add some extra information about them, so we'll do the conditional distribution. And density function. Okay. If we remember the probability of A given B, this is the conditional probability, where A is an event, B is another event. We said that this is the joint event of A and B, the probability of the joint event normalized by the probability of B. Now, let's take this and assume that let the event A to be A equals to x less than or equal small x. So our event is this one. So our probability of x less than or equal small x given B, we will call this to be fx of x given B. So this is the conditional distribution function. Now we took A here, we put it here, so this one will be like this, and definitely this is the probability of the joint event of x less than or equal small x and B divided by the probability of B. Okay, before we move further, let's discuss the properties of conditional distribution. All the properties that we discussed over the distribution itself also varied for the conditional distribution. I mean here by the following: fx of minus infinity given B, this should equal to 0. Fx of infinity given B is equal to 1. So any fx of x given B is greater than 0, less than or equal 1. So you are always between 0 and 1. Number 4, it's a non-decreasing function. So fx of x1 given B is less than or equal fx of x2 given B if x1 is less than x2. So even this one is less than, it could be less than or equal. So this is a non-decreasing function, non-decreasing function. So this is a non-decreasing function. Fifth property, the probability that x is between x1 less than or equal x2 given B, this is equals to fx of x2 given B minus fx of x1 given B. And the sixth, it's continuous from the right, so fx plus given B is equal to fx of x given B. So the function is continuous from the right. Continuous from the right. Okay. The second partner of the conditional distribution is the conditional density. So the conditional density fx of x given B is the derivative dfx of x given B by dx. So the density, conditional density, is the derivative of the conditional distribution. And the properties are the same as the 4 properties that we are given before for the original or the normal density function. So fx of x given b is always greater than or equal 0, which is the derivative of a non-decreasing function. So a non-decreasing function, it has always either positive derivative or zero derivative. To the integration from minus infinity to infinity fx of x given b. So the conditional density is definitely is a density. So its integration, the area under the curve is always 1. 3 fx of x given b. How, if this is the derivative, the conditional density is the derivative of the distribution, then the distribution is the integration of the density. So this is from minus infinity to x fx of z given b dx. And the last one, the fourth property, is the interval probability of an interval given probability of x greater than x1 less than or equal x2 given b is equal to the integration from x1 to x2 fx of x given b dx. Okay, those are the four properties, and they are exactly the same as the properties of the original distribution. Okay, I'm gonna go backward to the conditional distribution and discuss it a little bit further. Remember this equation here. I'm gonna leave it and work with it a little bit, because we put here A as an event, but what about B? Let us define some kind of B and see what will happen when we discuss it together. So I'm gonna keep this equation and study further the event B together with you. So let me just put it here. So fx of x given b is equal to the probability that x less than or equal small x intersection with b divided by the probability of b. Okay, we'll take this here. Okay. All right. So we'll define this as methods of defining conditioning events. We'll take the first type, 1. If we assume that b is equal to x such that it is less than or equal b, where b is some real number and b could be between minus infinity and infinity. Okay. Then what will happen? We need to evaluate this and put it in this form and find what will happen to fx of x. Okay, I'm gonna put, this is the real axis, x, and I'm gonna name that you have b here somewhere. So this is b on the real axis. Okay, now if I need to define fx of x, then this x that goes from minus infinity to infinity has two situations. The first one is x less than b, and the second one is x greater than b. Okay, if you say that x with b, it should satisfy both. So you can put it with anyone you want. So we go backward and say that, okay, we will have fx of x given, fx of x, given that x less than or equal b, which is our definition of b here. This should equal, now I'm gonna divide the answer into two parts, one for x less than b and one for x greater than b. Okay, so let's put it in this form. So if x less than b, so you have x somewhere here, then the intersection is the smaller. So if this is my x, so if x less than b, it's somewhere here, and this is what you need. The intersection of a and x less than or equal x. Intersection b is x less than or equal x. So this will be the probability of x less than or equal x intersection x less equal b divided by the probability of x less than or equal b, and this is equals to the probability of x less than or equal x divided by the probability of x less than or equal b, and this is equals to fx of x divided by fx of b. This is true when x less than b. So if x less than b, if we choose x here to be less than b, then you have from minus infinity to b, this is the event b. From minus infinity to x, this is the event a, which is x less than b, x less than or equal small x. So their intersection is the smaller one. So the intersection of this one with x less than b is equal to this one. So this is what we will get for this part. Okay? Now, if we go with x greater than b, so we'll choose x here. So this is, if my x is here, then the intersection of this period with this period is the smaller period. So this one here will be probability of x less than or equal b divided by probability of x less than or equal b, and this is equals to 1. See, and this one is true for x greater than or equal b. So if x greater than or equal b, this is true. And actually here, if x also equals b, then the fx of b divided by fx of b, and it's equal to 1. So this is what we will get. So our final result is fx of x given b. So fx of x given b capital, which is given that x less than or equal b, is equal to fx of x over fx of b if x less than b, and it's equal to 1 for x greater than or equal b. Okay? Okay, if we differentiate, then we can find the conditional density. So the conditional density what will happen here is we will differentiate So we'll have the derivative. This one is a constant. This is the variable x. So this is fx of x over fx of b, which is equal to fx of x over the integration from minus infinity to b fx of x dx. This is for x less than b. And 0, the derivative of 1 is 0 for x greater than or equal b. Okay? So this is if we define the interval or the b event to be less than or equal certain value of b. Okay, let's define the second method or the second way of defining b. I will keep this one. This is fx, fx of x. Okay, let's define the event in another way and see what will happen. Okay, so the second way of defining b, so b is equal to the event where x, random variable, is greater than b, less than or equal a. So it's a limited period. So fx of x, given that x is between b and a, is equal to the probability that x less than or equal x intersection x is between b and a divided by the probability that x is between b and a. Yeah. Now we will look at this. If we draw the line, the real axis x, we know that you have some b, some a, and this is your period or your event b. So the event b is here. Now we can have 3 segments of x. If this x is below b, then the intersection is phi, and the probability is 0. So if we choose x for fx of x, if we choose x to be below b, the intersection between x below b with this period here is phi. So the probability of phi is 0, and the answer is 0. If the value that we will pick for x is between b and a, somewhere here, so this is my x. So the intersection of those two is this one here. So this is the intersection. So it's the probability between b and x. This is the segment of intersection. Okay? If we choose for the third part for x to be greater than a, somewhere here. So if my x is here, then the intersection is the whole period divided by the whole period, so you end up with 1. Okay? So we will write this down. So you have 3 periods here. If x is less than a, if x is between a and b, and if x is if x is less than b, if x is between b and a, and if x is greater than a. Okay? So if x is less than b, then the intersection of x less than or small x and x is between b and a is equal phi. And this means that fx of x, given that x less than b less than or equal a, is equal 0 for x less than b. Okay? So this is the first part of the function. Fx of x, given b in the period such that x is less than b is equal to 0. Okay? It's a probability of phi. Okay, if x is greater than or equal b less than a, then the event x less than or equal small x intersection with x is greater than b less than or equal a is equal to, notice that we are here, so it's between x and b, so this is the random variable is between x less than small x. So the random variable here will be x is less than or equal small x, and this is how it looks like, and hence fx of x, given that x is between b less than a, is equal to the probability that x is greater than b less than or equal x divided by the probability that x is between b and a, and this equals fx of x minus fx of b over fx of a minus fx of b, and this is for x greater than or equal b less than or equal a. Sorry, for between and less than a. Okay, so this is the second segment. So this is number 2. And the last one, if x is greater than a, if x is here in this region here, if x starts to be larger than a, then the intersection of the two events, then the intersection of x less than or equal small x intersection with x between b and a is equal to the whole b, which is x less than b greater than a, and we'll take this to find fx of x given b, which is x greater than a less than or equal b is equal to, sorry, b into a. Is equal to the probability that x is greater than b less than or equal a over probability of x greater than b less than or equal a, and this is equals to 1 for x greater than or equal a. Okay, so we have 3 segments here, and we have the distribution functions. Just to put it in a nice form, let's write it down here. So we can say that fx of x, given that x is greater than b less than or equal a, is equal to 3 segments. It's equal to 0 for x less than b. It's equal to fx of x minus fx of b over fx of a, fx of b for x between b and a, and it's equal to 1 for x greater than or equal a. Okay, so this is how it looks like, and the corresponding density function f(x) of x, given that x is between b less than or equal a, is equal to, notice that the derivative of this one is 0, the derivative of this one is 0, so we have here the function, the derivative of this one is 0, so this is f(x) of x normalized by the integration from a to b, which is a constant, by the way, f(x) of x dx. This is for x between b and a, and I think this one should be between the integration between b and a. If a is larger, I'm sorry about this, from b to a, yeah, the integration from b to a, and 0 otherwise. Okay, so this is some information about the conditional, and you can find out that those conditional densities and distribution always satisfy the properties for any distribution function. The distribution function has 7 properties, the density function has 4 properties. They are all satisfied even with the conditional density and conditional distribution. Thank you very much for listening, and I hope you will find this lecture interesting. Thanks.